Hey, and welcome back to Discrete Mathematics. This week we're going to be talking about sort of the using our logic concepts in mathematics. And so sort of combining the two in a way. Honestly, this week is going to be a lot of just defining terms for things that you've probably heard of, but maybe haven't defined formally for yourself. And then we're going to take those terms and sort of use them in this sort of example axiomatic system, a new system. We'll talk about what those things are in a second, but to actually see how these would sort of play out. So the idea here is that in mathematics, there are some statements, and we've already looked at some statements that have sort of specific definitions, right? But there are others like theorem and definition and proofs and axioms and things like that that have a very specific meaning in mathematics. They're sort of special, and they play into sort of the logical structure of a system that you're creating in order to be able to prove new things, right? And so we can start with one of the first ones, which is a definition. Whenever you're defining a new mathematical system, right, you're going to have to create a lot of definitions. These definitions are not descriptive, right? They're not like the way you would define an English word, right? Like there is, an animal out there. It is a dog. I have to give it a name, so I give it a name dog, and then my definition just describes something that exists. These definitions really create brand new concepts, right? I am defining this new thing. I'm stipulating that this is the relationship between these two things or whatever. And so definitions will stipulate new meanings for either a term, symbol, object, whatever. It's just a new thing. So here we have an example. Two lines are parallel if they have no points in common. Now you understand what parallel lines are, and you know that that's true. But here we're not sort of describing parallel lines. You're now defining, stipulating what it means to be parallel. What it means to be parallel is that two lines have no points in common. So this definition is not describing one aspect of parallel lines. It is the definition of what it means to be parallel. If you say that something is parallel, you are saying that A and B have no points in common. That's important because you have a lot of other ideas about what parallel lines are, what they do, how they work. All of that stuff has to stem from that definition. But for right now, because we've defined it in this sort of limited way, when we say that two lines are parallel, all we're saying is that they have no points in common. Now, we know what that means, right? We know that they have to be parallel, right? They can never intersect. If you were to extend them out forever, they could never intersect. But, that would have to, all the other things you know about parallel lines have to come from that definition. For instance, like we already know what it means to be even and odd. And if I were to ask you, hey, what makes a number even? I might get different answers from different people because you know what even and odd mean, right? Even just means it's divisible, by 2. Or maybe you would say that, you can evenly divide it in half without, using only integers or something. There's lots of different things that you can sort of picture. What's an even number? Well, it's not an odd number. Everything I've said is true. But for our purposes, it's not the definition of what an even number is, right? We have to be a little bit more concrete. So we could define it in this way, right? An integer n is even if n equals 2k for some integer k. In other words, if there is some number that you can multiply by 2 and get the number, it's even. By the way, that also means that because it's a multiple of 2, it's evenly divisible by 2. But that's actually a corollary to the definition. We would have to prove that, right? All we know when you say a number is even is that there is some k that you can multiply by 2 and get the number, right? Everything else that you know about even numbers, the fact that a number cannot be even and odd, all that sort of stuff has to come from that definition. Similarly, the number's odd is just 2k plus 1. There's some k that makes that true, right? Which makes sense. You add 1 to any even number and you get an odd number. We know that, but that's not the definition. So, because these definitions are very precise, right, that makes them somewhat limited. In English and sort of thought in general, right, you can generalize, you can extrapolate, you can, that these two things are the same. Like, we know that, saying that something is in the form, 2k is the exact same thing as saying, it's, divisible by 2. But again, because we are sort of formalizing this, we have to start with the definition first and then hit everything else through some sort of logical steps. So the thing about definitions is they are stipulative, right? So they are saying, hey, I'm saying that this is equal to this. Like these two things are the same. I'm defining a term as this, which means that it's true sort of both ways, meaning that the relationship between those two concepts, the term and the condition, are an if and only if type of a statement, right? The implication goes both ways. If a number, matches the form 2k, you can find a k such that 2k is equal to the number. That is the exact same thing as saying it's even. If that's true, it's even. If you say it's even, that means that there is a k such that 2k will equal the number, right? The implications go both ways. Your most basic definitions are all going to be in the form of something is defined as this new term if there's some property that it has, right? A robot is cattywampus if some condition about the robot, right? It doesn't follow Asimov's rules. Okay, there we go. We've just defined something, right? A robot is cattywampus if it does not follow Asimov's rules. So if we were to take that and formalize it, right, we could say that d of x is the defined term. Robots are cattywampus, right? So something is cattywampus if it does not follow Asimov's rules, right? That's the p of x. That's the property that it must have. If it doesn't follow, Asimov's rules, if you don't know who Isaac Asimov is, I'm sorry. He's a famous science fiction author who wrote some very famous rules for robots. Anyway, Google it. We live in a modern era. So we have d of x, we have a p of x. So then when you create a definition, what you are saying is, sort of in predicate logic, right? For all x, p of x, if and only if d of x. In other words, if you are cattywampus, that means you do not follow Asimov's rules. If you do not follow Asimov's rules, you are cattywampus for every single robot that exists in the world. That's a definition. We are defining something to be true. A new concept called cattywampus that actually has an English meaning, but, I do these things in one take, and I'm just sort of flying off the seat of my pants. So you don't get the best examples all the time. But, right, there you go. It's for all x, that property implies, and if and only if, the implication is both ways, that term. So, other terms. We've talked about definitions a lot. Here's one that's kind of more weird, but somehow simpler. Axioms. Axioms are just things that are so fundamental that we can't really define them, right? I mean, like, you can. If n is a natural number, so is n plus 1. Like, I can define that, but I have to just take it as an axiom, right? I can't prove it. Like, it's because that is, in a way, what natural numbers are. Like, we define natural numbers by that idea that you just keep adding to the natural numbers and you will always get a new natural number, that they go on forever. This is true for a lot of things, right? Even just sort of in concept and philosophy. Like, there are some concepts that are so fundamental, you just have to take them as given without being able to show proof for them, because you need to have some language to start with. And so, what is a number? What is a number is an axiom, right? It's something that we start with. In fact, we would probably even break it down into natural numbers and real numbers and stuff like that. But, that basic concept that you might have asked as a child at some point, like, what is a number? Like, what does it really represent? So that, it's not a thing, it's sort of a quantity of things, but like, it's the idea of quantity in general. But I can't prove this, right? I can't prove you that 5 exists. We just assume that it does. So axioms are kind of on that basis. And here's the idea. Any theory in math is always going to be based upon some set of axioms, right? We have to say that these things, we assume these things to be true because we can't prove them because they're so basic, right? Numbers exist, right? And so because we assume that numbers exist and we understand what they mean, we can sort of start going from there. But yeah, everything is sort of a set of axioms. And by the way, it can get much more complex than that because you may be creating a system where it's like, yeah, I have to sort of define like, I don't know, network topologies, and I have to just assume that there's a thing called a connection, you know? What is a connection? Actually, connection is probably a better term for something else, but regardless, axioms, something so fundamentally true, we just have to assume it's true without proof. A theorem is a different type of statement. So a theorem is a statement that logically follows from any set of axioms and definitions and other proven theorems. So once I have sort of that system of here's the things that are so fundamental, I have to assume they're true. Here's a bunch of things that I'm defining as I sort of create this new system to define this new type of mathematics, whether that's plane geometry or linear algebra or, you know, I don't know, network topographies, right? You're defining these terms. And so a theorem is then based on those assumptions along with other theorems you've proved along the way. You're sort of developing stuff as they come out. Now, theorem is sort of a more general term. It's often what we'll use, but there's a few theorems that sort of like subsets of theorems, right? So a lemma is basically a theorem. It's something you've proven, but like sometimes when you're trying to prove something, you have to prove three other things first. Like if I can prove these three things are true, then I can prove that this overall thing is true. So that means I have to do a proof to come up with this true statement. Instead of calling this, you know, my theorem, because my theorem is the thing I'm going for at the end. It's the thing I'm trying to prove. It's what I put at the top of my paper, right? You know, like this is, I'm doing a, a graduate thesis to try to prove this thing, right? So the thing that I proved along the way is called a lemma. It's like, it's not the thing I'm going for. It's part of the thing. I have to prove this to be true first, and then I can prove another thing to be true first, maybe another lemma. And then based on the combination of these lemmas, I can then prove this last thing. So a lemma is sort of like, it's like a landing on your stairs, right? I've walked up some stairs. Hey, I'm kind of at a stopping point. Like I've done this. Now I just have to do the next set until I get to the next landing. I guess as you're proving something. Not a great example, but it's a proof that is part of a larger proof. A corollary is, in fact, I think I've already used the word today. So a corollary is something that is really, really related to the thing you proved. So like, here's my theorem I'm trying to prove. Once I prove that theorem, you know, there's this other thing I can prove too that's a corollary. Like they're basically the same thing, like with like one or maybe like two small steps, I can get from this to this because they kind of mean the same thing. That would be a corollary. In fact, I think the thing I used it as an example, or when I used the word, it was, you know, if even is defined as anything where you can find a k such that 2k is equal to the number, then it's even. Now, by the way, it's kind of a corollary that anything even is divisible by 2. And you could probably get there in 1 or 2 steps. It's a corollary. It's kind of saying the same thing. It's just that it's not the thing I'm trying to prove, but once I proved this, I kind of also proved this other thing. And then claims and conjectures. So a claim is just anything you're trying to prove, right? I'm starting out my proof. I have a claim. I say that this is true. I'm going to try and get through it. A conjecture is kind of interesting because it's something, because you would think that everything starts out as conjecture. But a claim, right, there's an assumption that like I'm going to get to the end of this proof and it's going to be proven. A conjecture, or I started with something and I can't prove it. So like I intended to prove it. It's a claim, but it's never going to become something else. A conjecture is something that we kind of know to be true. Like we suspect it's true, right? But we can't prove it. Conjectures are actually they deserve a lot more than just one line on a slide. There are some really famous conjectures out there, which, it's been a long time since I've taken math. I want to say it's not Goldberg, Goldbach. The Goldbach conjecture, right? One of the more famous conjectures in all of math. It's been around since like the 1700s. And it basically says that any even integer 2 or past 2, you can define as the sum of 2 primes, right? And it's true. 4 is 2 and 2, right? 6 is 3 and 3. 8 is 5 and 3. Hi, thank you. I can do basic math in my head. 10 is 5 and 5. 12 is, I should know this, 7 and 5. And point being, just trust me, it's going to be true. You can do it. We know it's true. Like, we can go as far as you want, and we can always, but we can't prove it's true. It's famously unproven. There is no proof, even though we can demonstrate it from 0 all the way up to God knows how large a number. We can't say that it's true all the way to infinity, because we can't test all the way to infinity, and we can't prove it to be true logically. Therefore, it's this true thing, but it's still called a conjecture. A very famous conjecture that if you ever find the proof for it, well, congratulations on your Nobel Prize. But regardless, conjectures, they deserve more than one line. All right, now counterexamples are going to feel probably a little intuitive, right? Because we kind of have an idea of what a counterexample is. If you have a mathematical statement, right, that says, I claim that for all x, p of x, right, whatever this claim is, that all odd numbers give me the Ghiblies, then the negation of that form, right, would be that there exists an x such that not p of x, right? These two statements cannot both be true. If I say all odd numbers give me the Ghiblies, and then you find an odd number that does not give me the Ghiblies, whatever that means, right, then if the negation is true, the opposite cannot be true. And so that we would call that a counterexample, right? That number that you gave me that is in that form, can't do it. If you wanted to look at Goldbach's conjecture, right? If you can find an example of an even number greater than 2 that can't be defined as 2 primes added together, then congratulations on your Nobel Prize. You just disproved it, but you're not going to, right? Point being, counterexamples. And so here we've got an example. If every prime number is odd. Here is a statement. Every prime number is odd. Well, 2 is a prime number, and it's not odd. So therefore, there exists something that makes not p of x true. And if that's the case, then the claim that every prime number is odd cannot be true. So we'd call this particular value a counterexample to the statement. Counterexamples are, I guess, a really short way of proving something to not be true if you can do it. And so that sort of brings us to all these definitions. Let's bring them into an axiomatic system. Axiomatic system is sort of like hey, I'm going to define something, a system, whether that's, fluid dynamics or plane geometry or whatever it is, right? And it could be simple network topographies. What are connections and nodes, and how can I prove that this is the fastest way to connect these two particular nodes or whatever. You can make up your own axiomatic systems, and so the idea is that when you do that, you want to define things very clearly. What are the assumptions? What are the axioms that you're using for your system? And then every theory has to sort of be pulled from those definitions and axioms and previously proved theorems. But even with that, you're still going to have this other thing, these undefined terms. And it's just because you have to start with something. You have to start with some sort of language. And sometimes you can express that as an axiom, and that's great. But sometimes you can't. If I were to ask you what a point is in sort of, geometry, you can define it probably, but you're going to be defining it in other terms that have to be defined, right? So like no one definition is probably going to be sufficient. You're going to talk about coordinates, but then we have to define coordinates. Well, how do you define coordinates without defining points? It's like at some point we sort of, the system itself, as you're creating multiple axioms and multiple definitions, you're going to like sort of, I get what a point is now. Like you've defined it, but it had to be defined over time. We just had to start out with a word, which is why I used some nonsense words to define some of these other things, because you can create an axiomatic system using nonsense words. You just have to start defining them. So that an axiomatic system is just the collection of all of those undefined terms and axioms. And then, later on we'll add definitions and theorems and all sorts of stuff that you sort of create. And it could represent whatever your problem set is, right? Your problem set is probably not going to be, I'm sure somewhere there is an axiomatic system for warfare. There's probably an axiomatic system for all sorts of stuff, right? You can create these things so you can talk in a formal way about things that aren't just, the math you took in high school. So here's an example system. we're going to create an axiomatic system. This is straight out of the textbook for a 4-point geometry. It's a geometry that only has 4 points. We got some undefined terms. I can't tell you what a point is. Like, we just have to know that that's a word. By the way, I didn't have to call it a point. We called it a point because I used the term geometry, but like we could have called it a spot or a location or a node or a whatever, right? But there's a point. There's also a line. There's also this term is on, right? These are undefined terms. They will be defined as we create the axioms, as we create the definitions, as we create the theorems. You'll get a sense of what those things are. But for right now, we just have to accept them as given. So then we've got 4 axioms for this system. For every pair of distinct points x and y, there is a unique line L such that x is on L and y is on L. So for any 2 points, there is a line that connects them. Any 2 points. Given a line L, axiom number 2, given a line L and a point x that is not on L, there is a unique line M such that x is on M and no point on L is also on M, right? So if I have a point x and a line L, right, there is a unique line M, a second line, such that x is on M and no point on L is also on M. So these 2 lines, L and M, don't share any points in common, right? Third, there's exactly 4 points. That's it. 4, it's impossible for 3 points to be on the same line. So you can never have 3 points on the same line. Only 2 points can be on a line at a time. So then that gives you a lot of different possibilities, right? But these are the axioms we sort of start with. And so these axioms, we are even with that assuming some stuff, right? I used numbers. I talked about 3s and 4s, right? Like, those numbers come from another axiomatic system, right? The set of real numbers, actually technically the set of natural numbers, right? But like, it comes from another set. And so I can kind of include these other systems into my system if I want to. I can actually define them axiomatically so that everything stays there. But sometimes you just sort of assume you're basing your new system on systems that came before. Yeah. And so, we've got some terms. We also use logic terms, right? So we're pulling from logic that, we didn't define that system. We're pulling from another system as well to create this new system. And that's okay. So we can also create some definitions, right? Some of these are just going to be definitions that make it easy. Like, we have this idea of a point is on a line, but what does it mean to be is on? Like, we never defined that. It was one of our undefined terms. But here we can say, well, let's start at least with the relationship. If a point is on a line, then we can say that that line passes through a point. Okay, so now I got, in addition to the relationship of points to lines, I now have the relationship between lines and points. So now I can say, instead of, the x is on L and y is on L, I could say, oh, there's a line L that passes through both x and y, right? I've got sort of that relationship going back and forth, and that's going to start to define what it means to be is on as we, keep on defining stuff. I'll create another definition. 2 lines L and M are parallel if there is no point x such that x is on L and x is on M. Sorry, for 2 lines L and M, they're parallel. If there's no point x, they don't share any points, right? Which means that now that second axiom, which sounded a lot like our definition of parallel lines, is now formally parallel, right? Like, given a line L and a point x that is not on L, there's a unique line M passing through x such that M is parallel to L, right? They don't share any points in common. So now we've got some axioms, we've got some definitions. We can actually start to make theorems in this new system that we've created, right? So theorem, 1, right, 1.1. In this example axiomatic system, there are at least 2 lines, which makes sense, right? There's 4 points. You can never have 3 points on one line, so there has to be at least 4, or at least has to be 2 lines, right? You can have a point that goes through A and M, but like, there has to be more than one line, at least 2 distinct lines. Now, In order to get to that, though, because this is a theorem, it requires a proof. So we can say by axiom 3, there are distinct points x, y, and z, which is true, right? If there's going to be 4 points, you can take any 3 points and say that there are 3 points. This is sort of a lesser statement. By axiom 1, there is a line L1 that goes through x and y, right? So we know that's true. For any points, 2 points, there's a line that goes through them. And a line L2 that goes through y and z, right? These 2 points have a line that goes through them. But by axiom 4, x, y, and z must not be on the same line. So L1 that connects these two and L2 that connects these two must be distinct lines. And if there's at least 2 lines, then we've proven our theorem. There has to be at least 2 lines, right? Now we could use this theorem to maybe prove other things or go on in other directions, right? But that's the idea. This is the idea of creating that axiomatic system where we're defining some new form of math, not form of math, but like we're defining a particular, like we're describing a problem set, right? With these formal tools that we can then use to prove stuff. And so that's the process. We'll talk more about proofs next time, but there you go. Bunch of definitions, a little bit of a sort of weird thing, hopefully not too trippy. But if you have any questions, send me a message through Canvas, and otherwise I will see you online.